Vibration analysis. Time and frequency analysis technique. Single frequency with harmonics.
The second, third, fourth, etc. harmonics can be either in phase or out of phase with the fundamental. The phase relationships between the fundamental and the harmonics are valuable in diagnosing problems in rotating machines.
Failure to understand and use the time signal and harmonic phase can result in diagnostic errors. The same physics that permit two signals to add and subtract apply to a single frequency with harmonics. A harmonic is some exact multiple of a discrete frequency. The discrete frequency, called the fundamental, is the first harmonic. The second frequency, which is 2 times the fundamental frequency, is the second harmonic.
A single frequency without harmonics will have one positive going peak per time period, as indicated in Figure 1. The number of positive going peaks in one time period of the fundamental frequency identifies the highest number of true harmonics.
This is true for a single frequency with harmonics only and is true regardless of the phase relationships between the fundamental and the harmonics.
The amplitudes of the fundamental and the harmonics determine the amplitudes of the positive going peaks. However, the phase relationships of the harmonics to the fundamental determine the locations of the positive going peaks in the signal. For example, the top grid in Figure 7 contains a fundamental and second harmonic. The second harmonic is in phase with the fundamental and goes completely out of and back into phase with the fundamental once each time period of the fundamental. The bottom signal in Figure 7 is the result of the top two signals adding and subtracting. It is important to note several points. Number 1 is the amplitude of the positive going composite signal is doubled because both signals are the same amplitude, and the positive going signals are added. And number 2 is the amplitude of the negative going composite signal is less because one cycle of the second harmonic is 180 degrees out of phase with the negative going portion of the fundamental. Number 3 is the second positive going peak is at the bottom of the fundamental, and the amplitude of the composite signal is 0. Once again, the reason for this is both signals are equal in amplitude, and they subtract. And number 4 is the composite signal is truncated on the bottom or negative side. The time period for each frequency is marked on each grid. The phase of the fundamental is changed 180 degrees in Figure 8. The two signals are still in phase because the harmonics are referenced with respect to the fundamental, as can be seen in the top grid. Both signals in Figure 7 start at the maximum value. In Figure 8, the fundamental starts at the maximum negative value, and the second harmonic starts at maximum positive value. It is important to note that the phase of the harmonic in reference to the fundamental is at the start of the cycle. In Figure 7 and Figure 8, the harmonic is in phase with the fundamental. The highest point of both signals occurs at the same point. At any other point in the cycle, the harmonic goes out of phase and back into phase with the fundamental. The net effect of the 180-degree phase shift is that the fundamental in the top grid and the composite signal in the bottom grid are shifted 180 degrees. The overall effect does not change the shape of the composite signal. The phase relationship between the fundamental and second harmonic is unchanged. In rotating equipment, the signals in Figure 7 and Figure 8 are the same result as could be obtained by taking data on opposite sides of a motor. That is, the fundamentals would be 180 degrees out of phase, but the second harmonics would still be in phase with the fundamentals. Again, this proves that data can be taken from either side of a machine without affecting the phase relationships of the harmonics. The top grid in Figure 9 contains a fundamental and a second harmonic. The second harmonic is 180 degrees out of phase with the fundamental. When this occurs, the second harmonic is in phase with the fundamental when both signals are maximum negative, and out of phase when the fundamental is maximum positive. This can be seen because the signals add when the fundamental is at maximum negative amplitude and subtract at maximum positive amplitude. The result is a higher negative amplitude in the composite signal in the bottom grid, and the two positive going peaks are at the top. The top grid contains both signals and displays how they go into and out of phase as they did previously. However, the second harmonic subtracts from the fundamental at the start of the fundamental cycle. Please note the composite signal still has two positive going peaks that identify the fundamental and second harmonic. However, both positive going peaks are at the top of the signal. This can only occur if the second harmonic is 180 degrees out of phase with the fundamental. Several points concerning amplitude must be made for figure 9. Number 1 is, the zero to peak amplitude of the negative going peak below zero is equal to the zero to peak amplitude of F1 F2. Number 2 is, the zero to peak amplitudes of each positive going peak are equal to the zero to peak amplitudes of F1 F2. Number 3 is, these amplitude relationships are true only for two signals equal in amplitude and 180 degrees out of phase. These phase and amplitude relationships hold true for linear systems. However, most real applications contain nonlinearities, called distortion. The distortion can appear in the signal as a phase shift in one or more of the harmonics. Distortion of the signal can also generate additional harmonics in the frequency domain which are not true harmonics of the signal. Therefore, the number of peaks in the time signal must be checked for true harmonic content. Continuing with phase relationships, the next step is to observe a phase shift of 90 degrees. Figure 10 and Figure 11 contain signals with a plus 90 and a minus 90 degree phase shift of the second harmonics, respectively. In Figure 10, the composite signal still has two peaks per cycle, denoting the second harmonic. However, instead of a discrete high and low peak, the lower peak is shifted to the left, on the downward slope of the signal. Figure 11 has the same uneven peaks, except the lower peak has shifted to the right and is on the upward slope of the signal. It can also be shown that any angle between 0 and 180 degrees can be approximated by looking at the various phase shifts. For example, a positive phase shift of the second harmonic will move the lower peak to the left. As the phase approaches 180 degrees, the lower peak will approach the same amplitude of the higher peak and the signal will look like the signal in Figure 9. In addition to phase shifts, the amplitudes can change. Figure 12 shows the second harmonic changed to 1/2 the amplitude of the fundamental. The starting amplitude of the composite signal is still the sum of the two amplitudes, 1.0 engineering units 0.5 engineering units equals 1.5 engineering units. However, the lower peak is smaller and does not have a zero amplitude. The two signals do not cancel each other because the second harmonic only subtracts 1/2 of the fundamental amplitude when it is 180 degrees out of phase. After seeing the effect of changing amplitude in Figure 12, one can identify the effect of changing the amplitudes in other ways. Changing amplitude only affects the amplitude of the composite peak. It does not affect the number of peaks or the phase relationship of the composite. The signals in Figure 7 through Figure 12 illustrate the effects of changing the phase and amplitude. With Signal Analysis Program or SAP, the amplitude, phase, and harmonic content can be identified, and these phase relationships between the fundamental and harmonics contain valuable diagnostic information. For example, if the spectra from a machine contain only a fundamental frequency generated by rotating speed and a second harmonic that is in phase with the fundamental, the shaft may be bent. If the second harmonic is out of phase with the fundamental, the machine may be loose. If the second harmonic of gear mesh frequency is out of phase with the fundamental, the gears have a backlash problem or are oscillating. If the second harmonic is in phase with the fundamental, the gears may be bottoming out. A good rule to remember is that if the source of the harmonic is tied to the source of the fundamental, such as a fixed, geared, or bolted coupling, the harmonic should be in phase. If the source of the harmonic is not tied to the source of the fundamental, the harmonic should be out of phase. This is also discussed in more detail later. The addition of a third harmonic will now be examined, along with the effects of changing the phase and amplitude. Changing the amplitude changes the amplitude of the individual peaks, as with two harmonics. Figure 13 contains a signal with three harmonics. 3 positive peaks per cycle are present, indicating the three harmonics. The amplitudes of the positive peaks above 0 are equal to frequency 1 add by frequency 2 add by frequency 3. So, 1.0 engineering units and 1.0 engineering units and 1.0 engineering units equals to 3.0 engineering units. The high peaks occur at the fundamental frequency of 60 Hz. The lower peaks occur at the third harmonic frequency of 180 Hz. The signal in Figure 14 contains only the first and third harmonics. The negative portion of the signal is more pronounced because the second harmonic is not present to subtract out the third harmonic. In fact, one cycle of the third harmonic is in phase with the negative portion, causing the two signals to add.
The amplitudes of the negative and positive portions are equal to frequency 1 add by frequency 3.
So, 1.0 engineering units add by 0.5 engineering units equals 1.5 engineering units.
When the first three harmonics are distinctive, misalignment is indicated.
This fact was documented several years ago by VCI.
However, until recently, the differences between the many time signals that can generate the same spectrum were not evaluated.
These differences can now be explained because of the phase relationships of the harmonics. The phase relationships of the harmonics can significantly alter the time signal without affecting the frequency spectrum.
There are an infinite number of phase and amplitude combinations possible. Figure 15 through Figure 20 show representative signals that have been identified on live data.
For example, Figure 15 is a result of a misaligned, rigid coupling. Misalignment is indicated because of the distinct first three harmonics, which must be in phase because of the rigid coupling. If a rigid coupling is not used, the phase of the harmonics will change, depending on the coupling. If the coupling is rigid, it acts in a linear manner.
If the coupling is loose or non-rigid, it will appear nonlinear and out of phase. Figures 16 through 19 showing the single frequency with two phase-shifted harmonic.
Figure 21 contains a spectrum from a main turbine generator.
The time signal contains the basic features of the signal in Figure 20.
Three harmonics are present and the third harmonic is 180 degrees out of phase with the fundamental.
Note the signal amplitude is less on the positive half than the negative half.
This is a form of distortion called truncation.
Truncation occurs when the machine is more flexible in one direction than in the other direction.
The first three harmonics in the frequency spectrum are also distinctive. These spectral lines are the result of the three positive going peaks in the time signal. The low-level harmonics in the frequency spectrum are a result of the distortion in the time signal, and are not true harmonics.
The first three harmonics are true harmonics in this spectrum.
The time domain signal is necessary to verify which harmonics are true and which harmonics are caused by distortion. In this case, the distortion is caused by various nonlinearities and is not required for analysis of this problem.
Thank you.